Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 42, part A, and we are talking about the third part of univariate transformations or inverse transformations. So in the previous videos, we've discussed how to do transformations for discrete random variables or distributions. And of course, we're using an inverse transformation to do that. And then last time we saw how to use the CDF method, and again using an inverse transformation to find the CDF of, let's say, y from x. So if y equals u of x, some function of x, then we find the CDF of y, then we take the derivative of the CDF to get the PDF of y. So in this video, we're going to talk about the univariate transformation theorem. And this particular theorem is for one-to-one functions. So the inverse, a one-to-one inverse exists. In fact, if it's one-to-one, we know that an inverse exists. If it's many-to-one, there may not be a inverse function. Okay, so the first case that we're looking at is when x is continuous, we have a function on x which gives us y, and so we're going to look at this transformation theorem. And so let x have the distribution f of x, y equal the function u of x, and this is a one-to-one function of x. Then we can then take and solve for x, and we'll call that w of y, but that is u inverse of y. Okay. The reason that we're giving it this w is so that we don't have to write the inverse the whole time. But remember that w of y is u inverse of y. It's the inverse function. So then the PDF of y is given by y is equal to, now, f of w of y. So remember that this is f of u inverse of y times the Jacobian of the derivative of w, or the Jacobian of w prime of y. And we call this the Jacobian because it's a matrix, but in this case it's only one value, so it's a singular value. But we will expand this when we go to bivariate or multivariate. Okay, so right now, so this format is very similar to what we'll do when we do bivariate transformations. Okay, so we take and we plug in w of y. So for x, every value of x, we're going to plug in, instead of f of x, for every value of x, we're going to substitute in what x is in terms of y, and then times the absolute value of the derivative of this inverse function of y. And this is this PDF will have the space y of in B, our joint or our range of y. Okay, so A is the range or support of x. B is the range or support of y. Okay, and w prime of y is simply the derivative of w of y with respect to y, and again we call that the Jacobian. So let's do an example so that this makes a little more sense. By the way, not only is this called an inverse transformation theorem, it's also called the change of variable technique or the change of variable theorem. Let's use f of x equals 4x cubed, and x is between 0 and 1. And we're going to let y equal negative 8 times log x. And I believe this is the same example we did here, 4x cubed, and we did y equals negative 8 times log of x. So we're going to do that same example using the transformation theorem. And so we are going to take the inverse. So first we're going to solve for x. So the first thing we do is divide both sides by negative 8. So we end up with log x equals negative y over 8. And then we take and we take the exponent, we put this in the exponent. Each side becomes the exponent of the natural number e. We can, as long as we do the same thing to both sides of the equation, we keep the equality. And so e raised to the log x is simply x. So this is a fact that you need to know. Okay? And then we have x equals e to the negative y over x. That is our inverse transformation and what we're going to use. And so we're going to set that as w of y. W of y, which is equal to x, is equal to e to the negative y over 8. And y is going to be between 0 and infinity. So when we plug in, we did that last time, when we plug in for y equals negative 8 log x, when we plug in x is 0, then log x becomes negative or goes towards negative infinity. So you can't take the log of 0, but it approaches negative infinity. So negative times negative is positive infinity. And then if we plug in 1, log 1 is 0, so 0 times negative 8 is 0. So that's how we got the range of y here. Okay? And now we take the derivative of w. So w prime, so we're taking negative 1/8 e to the negative y over 8. And then we need to take the absolute value of that. So we get rid of the negative here. Okay? So we end up with 1/8 e to the negative y over 8, because e raised to any power is always greater than or equal to 0. Okay? So as we said here. Then the PDF of y by the transformation theorem is f of w of y times the absolute value of the derivative of w. And so we simply plug in for x here, x cubed. So we're going to plug in e to the negative y over x and then cubed. And then we multiply by the absolute value of w prime. Okay? And so we simplify, and we can combine exponents, and we end up with 1/2 e to the negative y over 2, and y is between 0 and infinity. And in our previous example, we ended up with 1/2 e to the negative y over 2, y is between 0 and infinity. Of course, we can write it as a piecewise function. So we could rewrite this as g of y equals, and then 1/2 e to the negative y over 2, 0 to infinity, and then 0 otherwise. Okay? So we get the exact same answer. Now, let's do another example. We're going to do x has the distribution f of x, which is uniform from negative pi over 2 to positive pi over 2. As I mentioned in the start of this section, in the previous video, there are many relationships between the different distributions. All right? And we are interested in those relationships. They make things easier for us. Sometimes we cannot calculate something using the distribution we're given, and we can transform it and make the calculation much easier. So that's the purpose of this. Okay. So we have x has a uniform between negative pi over 2 and pi over 2. So we want to find the PDF of y equals tangent of x. Okay? So if we draw tangent of x, y equals tangent x, between negative pi over 2 and positive pi over 2, then we get this picture here. And so it's good to know these functions and what they look like. So I should put negative pi over 2 is this point here, okay, which is not on the line. And so we have our asymptotes, our vertical asymptotes at pi over 2 and negative pi over 2. And we see that as x approaches pi over 2, y goes to positive infinity. If x approaches negative pi over 2, y goes to negative infinity. Okay? And so we have f of x is equal to 1 over pi. For the uniform, remember that f of x is equal to b minus a over, or 1 over b minus a, sorry. I was about to mix that up with the mean, but that's not what we want to do. 1 over b minus a. In this case, b is pi over 2, and a is negative pi over 2. And so this is 1 over pi. And then we have to put our space of x where it's defined, and a is from negative pi over 2 to pi over 2. Now, y is equal to tangent of x, and y, notice, goes from negative infinity to positive infinity. We can look at the graph and see that. We don't even have to plug in if we can graph it. So that's a very handy thing to do. This can make these things a lot faster, a lot easier, and a lot more accurate if you can graph it. So the transformation on the range of x. So now we have b is from negative infinity to positive infinity. We're going to solve this for x. Remember, we're doing the inverse transformation, so we take the arctangent of both sides. We get the arctangent of y, and then the arctangent of tangent of x gives us x. So when we take the inverse of a function of a variable, we get the variable back. And so that's what we want. And so this is w of y. So we take the derivative of w, which is w prime. And if you remember from calculus, the derivative of the arctangent of y is 1 over 1 plus y squared. And notice, because y squared, we have y squared, this is always positive. Always positive. So that means that the absolute value of w prime of y is simply equal to w prime of y in this one case. So that is not true always. In fact, in the last example, one of the last examples, we saw that was not true. So please make sure that the absolute value, that you're very careful with this. So g of y is now equal to f of w of y times the absolute value of w prime of y. So f of y is, or f of w of y, is the same as f of x, because there is no x in the uniform. It's just 1 over pi. And then we multiply by w prime of y here. And so we end up with something called the Cauchy distribution. And we'll talk more about that in the next section. But this is the standard Cauchy. And the standard Cauchy would be Cauchy, 0, 1. So y is a Cauchy 0, 1. 0 is the median, and this is the scale parameter. Okay, so that's it for this video. So we'll pick up here and do the next theorem, which is a k-to-1 theorem, in the next videos. So please don't forget to scan and upload your lecture notes before midnight of the date listed in the course calendar. You definitely want to update your formula sheets with these theorems and any other bits of information. You'll want to update your list of distributions. Yes, so I want to, before we go, I want to make a result here that you need to know. So these results are very important. So if x is uniform negative pi over 2 to pi over 2, y equal tan x has a standard Cauchy distribution. This is an important result. You'll need to know it at some point in the future, so you definitely want to make sure you write those down. Okay, so please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, please come to virtual office hours. If you need help before you can make it to office hours, by all means, email me, but I need 2 things. Email me the picture of the problem, because I may not have it handy, and 2, a picture of your work so I can see how you're approaching the problem. And I will be happy to help you then efficiently and quickly through email. Please take care of yourself and stay safe, and we'll see you next time.